Today, let us study about the controllability and observability. The term controllability and observability related with the state model. A system can be represented using a state model, and we can see whether the system is controllable or observable. To see this, we are going through this topic. Okay. Then what is meant by controllability? See the definition. A system is said to be completely state controllable if it is possible to transfer the system state from any initial state x of t0 to any other desired state x of t desired in specified finite time by a control vector u of t. That is, within the specified time, if we can change the system state from one state to another state, we can say that the system is controllable. Okay. If the system, we feel that the system is going to an unstable state, then we can change the input vector so that we can bring the system to a controllable state. That is the term controllability. Completely state controllable. See this. Okay. If a state model is given, we can test for controllability. There are two tests for controllability. One is called Kalman's test and another one is called Gilbert's test. In this video, I am going through Kalman's test. Okay, what is Kalman's test? Consider a state equation. X dot is equal to Ax plus Bu. Then, we are forming a composite matrix QC. What is QC? QC, the first column is B matrix, second column of QC is AB, then A square B. This continues up to A raised to n minus 1B, where n is the number of state variable or order of the system matrix A. That is, if the number of state variable is 3, we will have these three terms B, AB, A square B, that is A square. State variable is 3, therefore A square, n minus 1 is 2. Okay. A system is, then after forming this QC matrix, we can check the controllability by seeing a system is completely state controllable if the rank of the composite matrix QC is n. A rank of the matrix is determined by seeing the determinant. If the determinant of QC not equal to 0, we can say that the rank of QC is equal to n. If rank of QC is equal to n, we can say that the system is completely state controllable. That is, all the state variables, n number of state variables are controllable. It is one of the simplest tests, but the main disadvantage of this test is that we can find the state variable which is uncontrollable. We can't find. We can say whether the system is completely controllable or uncontrollable. And if not controllable, we cannot specify whether which element or which variable is controllable and which variable is uncontrollable. That we cannot specify. That is the main drawback of this test. Let's see what is observability. A system is said to be completely observable if every state x of t can be completely identified by measurement of the output y of t over a finite time interval. That is, within specified time, we can observe or we can measure all the state variables. Then we can say that the system is completely observable. One term is observability, another term is controllability. Okay. Here also, for seeing whether the system is observable, there is two tests. One is Kalman's test and another one is Gilbert's test. Here also, I am saying only about the Kalman's test. Okay, let us consider a system. X dot is equal to Ax plus Bu, y is equal to Cx plus Du. That is state equation and output equation together gives the state model of the system. Then here also we are forming a composite matrix. In the previous case we formed a composite matrix QC. Here we are forming a composite matrix QO. where QO is equal to C transpose A transpose C transpose A transpose square C transpose up to A transpose raised to n minus 1 C transpose. Here also n represents the number of state variables. Here we are seeing whether the system is completely observable by seeing the rank of the matrix QO. That is, if rank of QO is equal to n, we can say that the system is completely observable. That is, the determinant of QO not equal to 0, then the rank of QO is equal to n and the system is completely observable. If determinant of QO is equal to 0, the rank of QO not equal to n and the system is not completely observable. That is, if there are n number of state variables, some variables are observable and some variables are not observable, but we cannot say which element or which variable is observable and which variable is not observable. That is the main disadvantage of this test, but it is one of the simplest tests. Okay. This is all about Kalman's test for observability and controllability. Now, let us see an example. Here is a question. One state diagram is given. Write the state equation for the system and determine whether the system is completely controllable or observable. First, we have to derive state model from the state diagram, and then we have to see whether it is controllable and or observable. Okay. First stage, finding state model. We are taking each block one by one. The first block, output is x1 of s, and this block parameter 2 by s into s plus 1. Input to this block is x2 of s minus x3 of s. We know input into the scalar quantity inside the block is equal to output. Therefore, output x1 of s equal to x2 of s minus x3 of s into 2 by s into s plus 1. We are cross multiplying. Then after that, we are taking the Laplace inverse. While taking the Laplace inverse, s square terms represent the second differential, that is x1 dot. Then one s term represents first differential x1 dot. Therefore, x1 double dot x1 dot is equal to 2x2 minus 2x3. This is the time domain function. This is done using Laplace inverse. Now, taking the second block, s output input x1 of s, its output x3 of s. Therefore, s into x1 of s equal to x3 of s. From here, taking Laplace inverse, we get x1 dot is equal to x3. x1 dot is equal to x3. This equation is substituted in this equation. So, we get what is x1 double dot? x1 dot equal to x3. Therefore, x1 double dot is equal to x3 dot. So, x3 dot plus x3 is equal to 2x2 minus 2x3. From here, x3 dot is equal to 2x2 minus 3x3. From these two blocks, we got the derivative of first state variable, then here the derivative of the third state variable. And we also need the derivative of x2. If these three equations, that is x1 dot, x2 dot and x3 dot are obtained, then our aim is satisfied. So, to get x2 dot, we are considering the rest of the block. Here, the input is u of s minus x1 of s and output is x2 of s. Now, we are multiplying, then cross multiplying, then taking the Laplace inverse, we will get x2 dot is equal to minus 2x1 minus 3x2 plus 2u. From these three, we are writing the state equation. The state equation is this: x1 dot, x2 dot, x3 dot. And also, we know the output y is equal to x1. From that, we are deriving the output equation. Here A is the system matrix, here it is a B matrix and it is the C matrix. If A and B are obtained, we can check for controllability. If C and A are obtained, we can check for observability. Then first we are doing Kalman's test for controllability. First the composite matrix is formed, QC, B matrix. Okay, the QC matrix, see, first B matrix is written as the column matrix. Then we are multiplying A and B together. We will get a single column matrix. This is written as the second column of QC. Then A square B, again a column matrix. This is written as the third column of the QC. Then we are calculating the determinant of QC. We obtained it as 32. This is not equal to 0. Therefore, rank of QC equal to 3. Therefore, the system is completely state controllable. Similarly, we are testing for observability. For observability, we are forming composite matrix QO. We are taking A transpose, C transpose, then multiplying then these terms. Here also we see state variables are taken as 3. Therefore, A transpose square n minus 1 is equal to 2. Please see this. Okay. Is formed. Then determinant of QO. It is calculated as minus 2, not equal to 0. Therefore, rank of QO is equal to 3. Hence, the system is completely observable. Please see all these steps. Okay. With this, we are concluding